All right, after that first example of families of curves, we will do one more. First example was mainly to get the idea down. This one should be a little bit more interesting. It'll be a little bit more work, though, as you'll see. So we're going to look at the family of curves x to the m e to the px, where m is an odd integer greater than 1. So m is 3, 5, 7, 9, something like that. And p is some positive constant. We want to find the roots, so that's not a calculus problem. This just means 0 is equal to x to the m e to the px. So that means what? Either x to the m is 0 or e to the px is 0. If x to the m is 0, that's like saying x cubed, x to the 5th, x to the 7th, something like that is 0. That means x is 0. What about e to the px? That's one of our exponential functions, right? And the graph of this exponential function is always above the x-axis, so it has no roots. It has a horizontal asymptote at 0, y equals 0, but has no solution. So the only root is at x equals 0. E to the px is always positive. This is going to be something useful for us in the rest of the problem. Let's find the x values of the critical points and then decide if each one is a max, a min, or neither. So for that, we've got to take the derivative. And we can't forget all our normal derivative rules here. So what derivative rules are we going to need for x to the m e to the px? We are going to need two of them, right? We're going to need the product rule, and we're going to need the quotient rule. Not the quotient rule, the chain rule. Product rule and the chain rule. So the product rule says, doesn't matter which one I take the derivative of first. I've done this problem a lot of times, so I happen to know that things work out a little bit cleaner if we actually take the derivative of the e to the px first. But the answer will be the same either way. So I'm going to leave the x to the m alone. Now I've got the derivative e to the something. Chain rule says derivative e to the something is e to that same something, but the chain rule says you have to take the derivative of the inside function, meaning multiply by p. Then we take the derivative of x to the m, which is mx to the m minus 1, and we leave the e to the px alone. We should ask ourselves, can this ever be undefined? So x to the m minus 1, we should be a little bit concerned when we see that m minus 1 up there, wondering if this was enough to make that exponent negative, meaning to put the x into the denominator like it did in an example from last week, and therefore we'd be dividing by 0. So is it possible that m minus 1 is a negative exponent, and now we have the danger of dividing by 0 here? It is not possible, because m is an odd integer greater than 1. So the smallest that m can be is 3. So if I take a number that's 3 or more and I subtract 1, I still get a positive. So this is never undefined. So all we need to do is set it equal to 0. And we want to think about what can we factor out of this. We can certainly factor out an e to the px. And they both have some powers of x in there, right? So for a moment here, it might be easier if we actually pick some value of m. Suppose m were 7. This is x to the 7th. This is x to the 6th. What would we factor out if we had an x to the 7th and an x to the 6th? We would factor out the x to the 6th, right? So here we're going to factor out x to the m minus 1. So what's left from this first term is an x and a p. Because factoring out is basically dividing. So if I divide x to the m by x to the m minus 1, our exponent rules say I subtract the exponents. And if I do m minus the quantity m minus 1, I just end up with 1. So this is x to the 1. And the only thing left from this is an m. So now what are the solutions to this? As we just discussed, e to the px is always positive. It can't be 0. This is x to some power. So this is 0 when x is 0. And if we set this to 0, that means px equals negative m. So x equals negative m over p. So these are our candidates to be local extrema. And now we have to check to see if they are or not. And for that, we do our number line. So which side of 0 should negative m over p fall on? We know m and p are both positive, so negative m over p is negative. So negative m over p is somewhere over here, and then 0 comes over here. So I'm going to have to pick three numbers, a number here, a number here, and a number here. If I want to move a number farther away from 0, as we discussed in our last example, we can double it. So if I double this negative, it will move over to there. So a good number out here would be negative 2m over p. So I want to figure out the sign of f prime of negative 2m over p. All right, so what are we going to do here? First, we're going to take a negative number. What are we going to do here? Sorry, this is what we're going to. Which is it better to plug into, the factored or the unfactored? Definitely the factored form. E to any power is always going to be what sign? That's positive. 2.71828, raise it to any number, you always get a positive. Here, I've got a negative number, negative 2m over p, and I'm raising it to a power. So if I take a negative to a power, sometimes I get a positive and sometimes I get a negative, right? Do we have to do two different cases here, depending on whether we've got an odd or an even exponent there? Or was the problem written in a way to avoid that? It was, right? We know that m is odd. And if m is odd, what does that tell us about m minus 1? M minus 1 has to be even. So I've got a negative to an even power. And so a negative to an even power is going to be positive. And then I'm going to plug my x into here. So negative 2m over p times p plus m. So the p's cancel. So what are we going to get here? We're going to get a positive. A negative to an even power is positive. And now I've got negative 2m plus m, which is negative m, but m was positive. So negative m is negative. So we get positive, positive, negative, which is negative. So what do we know f is doing out there? F is decreasing because f prime is negative. And we mentioned this last time, but just to reinforce it, the reason that we only have to pick one number out there and we get every other number out there for free is because this derivative is a continuous function. The only way a continuous graph can change from a positive y value to a negative y value is by going through 0 or by having a discontinuity. There are no discontinuities. We said the derivative is always defined here. And we've already found all the places where the derivative is 0. So since there are no more places out here where f prime can be 0, there's no chance that the sign can change from negative to positive anywhere out there all the way to negative infinity. What's a good number to pick in here? As we discussed in the previous problem, if you cut a number in half, you move it closer to 0. So if I do f prime of negative m over 2p, that'll be in between. So e to any power is still positive. I've still got a negative, but it's to an even power, so that's going to be positive. And now I'm going to take my x, which is now negative m over 2p, times p plus m. So we get a positive and a positive. And now the p's cancel. We get negative m over 2 plus a full m, so that's positive m over 2, so that's a positive. So positive, positive, positive is positive. So that means f prime is positive in between here and here, so f is increasing there. So what have we found out about x equals negative m over p? That's where f has a local min. And now we need to pick a number out here. So here we actually catch a little bit of a break. Here we can actually pick a specific number because we just need to pick any positive number. So I can pick 1. I'm feeling very boring today. E to any power is positive. 1 to any power is positive. And then for the x, I'm going to plug in 1. So I get 1 times p plus m. But that's just p plus m. We knew p was positive. We knew m was greater than 1. M is positive. Positive plus positive is positive. And 3 positives multiplied together give us another positive. So what did this x equals 0 work out to be? Max, min, or neither? It worked out to be neither, right? Because the graph comes up, levels off, is perfectly horizontal for one instant, and then keeps going up again. So that's what we know. So f has a local minimum at x equals negative m over p, and neither max nor min at x equals 0. All right, so that was the local extrema. Are you ready for the inflection points? This next thing is probably the global maximum of the course in terms of algebraic difficulty. So get ready. We want the inflection points. We need f double prime. So let's just remind ourselves of what f prime was. F prime of x was x to the m times p e to the px. Up above we had written the p afterwards. Doesn't make any difference. Plus mx to the m minus 1 e to the px. So what rule or rules are we going to need for this derivative? Same ones as before, right? But we're going to need the product rule twice because this is a product and this is a product. So let's get ready here. F double prime. I want to take the derivative of this. Say I leave the x to the m alone. This p is a multiplying constant, so it stays. And the derivative of e to the px is what we just took in the previous part. That's e to the px times another p from the chain. Now let's take the derivative of this part. That's going to be an mx to the m minus 1 multiplied by pe to the px. So that was the product rule on this first part here. The second part is also a product, so we need product rule there. So I'm going to leave this first part alone, mx to the m minus 1. And now I got to take the derivative of e to the px. I think that's the third time we've done this in the problem. Nothing has changed about the laws of calculus. It's still e to the px times p. And now we have to take the derivative of mx to the m minus 1. The m is a multiplying constant, so it stays. The m minus 1 comes down. X now to the what? M minus 2. E to the px. Lovely. Let's see if we can simplify this a little bit. This is x to the m and a p squared here. So x to the m, p squared, e to the px. You'll notice that these two middle terms are actually the same. They both have mx to the m minus 1 and e to the px and a p. So I can just combine them into one and call it 2mp x to the m minus 1 e to the px. And then my final term over here, I can call it m squared minus m by multiplying those two terms together. X to the m minus 2 e to the px. We should ask ourselves, can this ever be undefined? E to the anything can never be undefined. We should consider, can x to the m minus 2, was subtracting 2 from m enough to make this a negative exponent and put the x into the denominator where we're in danger of dividing by 0? And the answer is no, because m is odd and greater than 1, meaning the smallest m could be is 3, and even 3 minus 2 will not give us a negative. So there's no danger that this actually became an x in the denominator. So what can we factor out? Suppose we knew what m were. Suppose m were 7, as in the previous, as I said before. This is an x to the 7. This is an x to the 6. This is an x to the 5. Which of those three would you factor out? You would factor out the x to the 5, right? So if we factor out the x to the m minus 2, that's the smallest exponent on the x here, smallest power of x. We can also factor out an e to the px from every one of those terms. So if we factored out x to the m minus 2 from x to the m, we're left with an x to the 2 from that. We can always check if we factored this correctly by multiplying it back out, right? And if I take x to the m minus 2 times x to the 2, from the very first week, our exponent rule says we add those exponents, and that gives us x to the m minus 2 plus 2, which is x to the m, which is what we started with, so that's good. So x squared times p squared. What's left here in the middle is 2mp x to the first power. If I had factored out an m minus 2 from x to the m minus 1, I've still got an x there. And what's left from this last term is just m squared minus m. All right. This thing here is what kind of function? It's a quadratic, right? So we know how to solve quadratics. We have the quadratic formula. So we're going to have to pause here for a second. So we're going to need to leave a little bit more room down here. We're going to try to factor this. So we're going to try to write this as x to the m minus 2 e to the px. I'm going to leave a little bit of space here. We'll talk about that in a minute. X minus something else. The quadratic formula is what's going to tell me what to put in these two boxes when I factor out, when I do the quadratic formula. So if I do the quadratic formula on this, let's just remember what the quadratic formula says. It says x is supposed to be negative b. So negative, this is the b, right? B is the coefficient on the x. So minus b, minus 2mp, plus or minus the square root of b squared, so 2mp quantity squared, minus 4ac. A is the coefficient on x squared, which here is p squared. And c is the constant here at the end, m squared minus m. And then it's all supposed to be divided by 2a, right? So all over 2p squared. Are you getting nervous? I hope this will simplify nicely. And by the way, if you have some other way of solving quadratics, like completing the square, that's great. You'll come up with the same answer either way. Let's hope this will simplify a little bit. So I've got a negative 2mp. And what have we got inside the square root here? If we multiply this out, 2mp quantity squared is 4m squared p squared. And here I've got a minus 4p squared m squared. And here I've got a minus 4p squared times minus m, so that's a plus 4p squared m all over 2p squared. Well, I hope you're starting to see that things are starting to simplify a little bit nicely, because 4m squared p squared, these are the same term, they cancel. And then I've got a square root of an almost perfect square, right? I've got a square root of a 4p squared in there. So if you've got a perfect square inside of a square root, you can pull it out. And when I pull a 4p squared out of my square root, what should it become on the outside? It should become 2p. And look at that. The only thing left inside the square root is an m. And we're still over 2p squared. So this is already getting a lot simpler. There was no reason to think when we started trying to solve this quadratic equation that we would get any sort of nice answer. But I hope you're starting to see that it is going to come out quite nicely. Because now all the 2's will cancel, and I've got a p and a p and a p squared, so those will cancel as well. So the only thing left from this first term is a negative m. The only thing left from this is plus or minus square root of m all over p. So what is that saying? That the roots are negative m minus root m over p, or, so that's just saying x equals this, or x equals negative m plus root m over p. So this really did simplify quite surprisingly nicely by doing the quadratic formula. So that's what we're going to put in here. X minus the first root, right? Because if I were to plug this number in for x, I would get 0 in here. Because I'm taking the number minus itself, that gives me just 0. That's what it means to be a root here. Or the same thing here, negative m plus root m over p. Now, why did we leave a little bit of space here? If we actually multiply this out, do we get what we had up above? And I hope you'll agree that we do not, because clearly when we multiply this out, the first term is going to be x squared, but it's supposed to be x squared times p squared. So, and the first time that I did this problem, I think I probably didn't realize this about the quadratic formula myself. But the quadratic formula it tells us the roots, but it doesn't tell us exactly how to factor it. For example, if you do the quadratic formula on 4x squared minus 4, I won't write out the details for you here. It will tell you that the roots are x equals 1 and x equals negative 1. But does that mean that 4x squared minus 4 is equal to this? It doesn't. There's no way that's going to be equal. The quadratic formula is leaving it up to us to remember that we have to put the correct coefficient out front. In this case, it would be a 4. So this is just an aside on how the quadratic formula works. It tells us what the roots are. We have to remember what the coefficient is. In many cases, we don't care what the coefficient is. All we care about is what the roots are, which is why many of us probably never paid attention to the fact that we do have to put this coefficient out front. So if I really do want to write an equal sign here, I need to put a p squared here so that when I do multiply this out, I get x squared times p squared like we are supposed to get. Good. All right. So what does this mean? if x to the m minus 2 is 0, so that's what we're trying to do here, right? We're trying to set this equal to 0. If x to the m minus 2 is 0, x is 0. Can e to the px be 0? No. E to the px is always positive. Can p squared be 0? No. P squared is always positive. And then these give me the two different roots. So x is 0, x is negative m minus root m over p, and x is negative m plus root m over p. So those are the three numbers we're going to have to put on our number line. We said this would be some challenging algebra. So let's make our number line. So which side of 0 should those two roots go on? They should both go on, well, definitely this first one, negative m minus root m over p. That's definitely the farthest to the left, right? That's the most negative of these, more negative of these two numbers. M is positive, and so negative m is negative. Square roots are always positive, so we're taking this top is negative and p is positive. Now what about this root, this one here, negative m plus root m over p? Is that less than 0 or is that greater than 0? We know m is bigger than 1. And if you take the square root of a number bigger than 1, you get a smaller number. So when I take negative m and I add only root m to it, that's not enough to make the numerator positive. So this is still negative, and then we get 0 out here. Let's remind ourselves about what f double prime was to help us plug in. F double prime was x to the m minus 2, e to the px, p squared, and then the two roots that we got, the two factors we got from the quadratic formula. Remember, you're analyzing a whole family of infinitely many curves here, so we expect it to be a little bit of work. Let's make a couple notes here. E to the px is going to be positive, p squared, those are both going to be positive, no matter what we plug in. So that's going to make our life a little bit easier. Let's plug in. I've got to pick a number to the left of this negative. So if you double a number, you move it farther away from 0. So if I double that number, meaning I take 2 times it, 2 times negative m minus root m over p. All right, let's see here. We're taking a negative number for x. We're raising it to the m minus 2 power. What did we know about m? M was odd. M minus 1 was even, so m minus 2 is odd. So this is a negative to the odd power. And a negative to an odd power is going to be a negative. When I plug this negative, I'm taking a big negative minus a smaller negative. And if you take a big negative minus a smaller negative, say negative 7 minus negative 5, you get a negative. And we're doing the same thing here. I'm taking a big negative minus a smaller negative. That's going to be another negative. So what did that all mean? We got a negative to an odd, which was negative. So a negative times a negative times a negative, which is positive. So we can go over here. Just kidding. Negative times negative is not positive. Last time I thought about it. Negative times negative is negative. This is live TV, folks. So where f double prime is negative out here, so f is concave down over there. All right, let's pick a number in between here and here. One way that's easy to pick a number between two other numbers is to take the average of those two. And when you average the two, the square roots will cancel each other out perfectly, and we'll just get negative m over p. So the sign of f double prime of negative m over p. That's halfway between the two roots in the quadratic formula. And you might notice, you might find this familiar using the formula that you know for finding the vertex of a parabola. But that's not, we don't really need to worry about that right now. We're still taking a negative here to an odd power. These two terms still here are both positive, so I'm not bothering to write them. Right? I could have written a plus and a plus here, but they're not going to change the sign. And now I'm taking remember, I'm taking a negative number between here and here, and subtracting a more negative. So let's think about that. You take a small negative minus a big negative. So -5 minus -7, that's -5 plus 7, that's going to give us a positive. Now here I'm taking a bigger negative, right? I'm taking a negative in here minus this negative. So a big negative minus a smaller negative is a negative. So what does that all tell us? A negative to an odd is negative. Negative, positive, negative is positive. So f double prime is positive here. So f is concave up. So we found ourselves at an inflection point. We changed from concave down to concave up. We've got to pick a number in between here and here based on what we've done before. If I cut a number in half, it moves it closer to 0. So if I take f double prime of -m plus root m over 2p. So I'm still taking a negative to an odd power out here. I've still got two positives here, which I'm not writing. And now in both of these cases, I'm taking a small negative minus a bigger negative. And if you take a small negative minus a bigger negative, in both of these cases, you get a positive. So we got a negative to an odd, which was negative, times two positives, which is negative. So we found ourselves another inflection point. This is the hardest algebra we're going to see all semester. Don't worry. And now finally, we get a little bit easier thing. We can pick some positive number. Let's pick something fun. Let's pick pi. So now, this time, now I've got a positive to an odd power. And a positive, whether it's to an odd power or an even power, doesn't matter. I'm going to get a positive. And in both of these cases, both of these are still positive. I'm not writing them. And in both of these cases, I'm taking a positive minus a negative. And you can check for yourself. Anytime you take a positive minus a negative, you always get a positive. So we got positive, 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 which was positive. So we found another inflection point. So f had 3 inflection points. So f has inflection points at x equals -m minus root m over p, x equals -m plus root m over p, and x equals 0. Wow. Look at that. You should look back at that second board or your notes and think how far you've come since the beginning of the semester, how much progress we have made. Part D. This is one of these 4 chalkboard problems. We want to sketch this graph. You'll notice that everything was happening in the negative side. So I'm just going to draw, this is what my f is going to look like. The interesting points, we had an inflection point at -m minus root m over p. We had a local min at -m over p. And we had another inflection point at -m plus root m over p. And we had a root from part A at 0. Only one root. That was the only root for the entire function. So I'm going to start here, and I'm going to work my way backwards. We'll see why in a minute, I hope. So if you look back at the number line from part B, from 0 to the right, we're supposed to be increasing, and from part C, we are supposed to be concave up. So the graph should be looking like this. And the slope there was 0. If you look at the number line from part B, we're still increasing in this region, but from part C, we're concave down. So I want to be increasing concave down. So we see that not only did we have a root at 0, we had an inflection point. If you look back at the number line from part B, we're still increasing in this region, but we're concave up. And now if you look back at the number line for part B, all of this time we're supposed to be decreasing, and we're still concave up. So I'm decreasing concave up. So this was our local min. This is going to be an inflection point. And the two number lines together tell us that all the rest of the time we're supposed to be decreasing concave down. So let me draw this very lightly here. If I draw this, is that possibly the right answer? Is that possibly what the graph is supposed to look like? It's got the right shape. It's concave down out there and decreasing. But this violates one of our parts, part A. Part A, we found there was only one root, and that was at x equals 0, meaning we cannot cross the x-axis again out here. So this is not possible. So we have to erase that. So the only thing that can be happening over here is a horizontal asymptote, because I've got to go off to the left forever, and I've got to be going upward as I go to the left, but I can't cross the x-axis. So we're going to get some horizontal asymptote. Now I've drawn it as if the horizontal asymptote is at y equals 0. We don't actually know that. So if we want to actually check that, we would like to see what is the limit as x goes to negative infinity of our function. As x goes way, way off there, we know we're going to get a horizontal asymptote. We don't yet know. I mean, if you trust me, it's going to be at y equals 0. But let's see if we can actually figure it out. And I want to do this because it's going to use one of our nice rules. X is going to negative infinity. And our function is x to the m e to the px. This is actually an indeterminate form. Not one of the indeterminate forms that we've already looked at, but it is. If I'm taking a huge negative and I'm raising it to an odd power, this part here is going to negative infinity. P is positive, so this is e to a huge negative. So if you imagine like e to the negative 1,000, that's the same as saying 1 over e to the 1,000. So this is going to 0. And although 0 times any number is always 0, 0 times something going to infinity is not necessarily 0. It depends on which one's going faster, as in all of these indeterminate forms. We wish that we could use L'Hopital's rule. But L'Hopital's rule only works when we have a fraction, 0 over 0 or infinity over infinity. But in many cases where you get an infinity times a 0, you can rewrite it as a fraction. So I can keep the x to the m on the top, and what would I have to write this on the bottom? If I bring this to the bottom, that's like saying 1 over e to the px down here, which is the same as saying e to the negative px. This is the same as saying 1 over e to the px. So if I divide by 1 over e to the px, that's the same as just multiplying by e to the px. So this is exactly the same as this. But the nice thing is that now the top here is going to negative infinity, and the bottom is going to positive infinity, because I'm plugging in a negative for x. So I'm taking negative p, a negative number, times a huge negative. So this exponent on the bottom is a huge positive. So I'm taking e to a huge positive, which is going to infinity. Now what's going to happen when we do L'Hopital's rule? How many times are we going to have to do L'Hopital's rule? You can ask yourself this question here. When I take the derivative of the top, I'm going to get what? Mx to the m minus 1. And on the bottom, I'm going to get negative p e to the negative px. This is still going to be the same thing, negative infinity over infinity, because I'm still going to have this x on the top. So if you think back to the problems that we did earlier with L'Hopital's rule, somehow I need to make this thing on the top become just a constant. And if we keep doing L'Hopital's rule again and again and again, eventually this will come down. There will be an m, and then an m minus 1, and then an m minus 2, dot, 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 and then a 3, and a 2, and a 1. If I started with x to the m, so imagine that we started with x cubed. How many times did we need to do this? The first time x cubed went to 3x squared, then it went to 6x, then it went to 6. So if I started with an x to the 3, I had to do 3 times here. So if I started with x to the m, I did L'Hopital's rule a total of m times here. So what happened here, m of these negative p's came out. So I get negative p to the m e to the negative px. This thing on the top is written as m factorial. You might have seen that. But it's a number. This is some number. And the bottom, this is going to infinity. M is odd. So this is a negative to an odd. So the bottom is going to negative infinity. So I've got a number over negative infinity, which is 0. So L'Hopital's rule came to the rescue for us here. I know it was a little bit complicated, but that's what lets us know that this horizontal asymptote truly is at y equals 0. L'Hopital's rule, by letting us turn this other indeterminate form, negative infinity times 0, into infinity over infinity, with this negative sign out front, which we don't really care about. We can just pull a negative out front. Did you enjoy that? That was the hardest algebra of the semester, as we said. So anything after this will not be as messy algebra. And we have an applet for you to explore this lovely family of curves. Please enjoy that.